ఓకే. Sir, Kishore got just 5 minutes, sir. Kishore got 5 minutes only, sir.
No problem.
Thank you, sir. Thank you. అంటే నేను షెడ్యూల్ పంపించాను కదా, షెడ్యూల్లో అంటే
పార్టిసిపెంట్స్ అని ఉంది కదా సార్, దాన్ని ఆన్సర్ చేయండి సార్. ఎందుకంటే యూట్యూబ్ లైవ్లో అది వచ్చేస్తుంది సైడ్లో.
ఒకసారి
అక్కడ వెబ్ఎక్స్ సిస్టమ్ వెబ్ఎక్స్కి వెళ్ళండి. ఇక్కడ పార్టిసిపెంట్స్ మధ్యలో బ్లూ కలర్ ఉంది సార్.
క్లోజ్
పార్టిసిపెంట్స్ చేయండి సార్ ఒకసారి. ఇప్పుడు యూట్యూబ్ లైవ్లో ఓన్ ఆయన లైవ్లో పక్కన మన వచ్చేస్తుంది, అవసరం లేదు కదా సార్.
అంటే నాకు అర్థం కాలేదు సార్.
ఇప్పుడు ఇలా వస్తుంది సార్. ఇలా వచ్చిన తర్వాత యూజువల్గా సిస్టంలో మీకు ఎలా కనపడిందో పార్టిసిపెంట్స్ మీద క్లిక్ చేయండి మంచిగా దాని పక్క ఇలా యూట్యూబ్లో వచ్చేస్తుంది. ఇది అవసరం లేదు
కదా. అంటే మన చాట్ బాక్స్ లాగా వస్తుందా?
ఆ తర్వాత కావాలంటే పెట్టుకోండి చాట్ బాక్స్.
ఓకే,
అది కూడా కనపడుతుంది. అది యూట్యూబ్ లైవ్లో అవసరం లేదు సార్. అన్సెలెక్ట్ చేసింది ఓన్లీ సార్ ఒకటి కనపడతారు, ఆయన పీపీటీ
రైట్ సైడ్ మనకు అవసరం లేదు.
అవసరం లేదు ఇంకా
ఈ కంప్లీట్ ఉండాలండి.
మరి ఎక్కడ వచ్చినప్పుడు
నాకు కొద్దిగా అలా ఇంటిమేషన్ ఇవ్వండి. పార్టిసిపెంట్స్ అనేది మనం ఎవరెవరు జాయిన్ అయ్యారు అనేది ఒకసారి చూసుకోవాలి కదా. మన లిస్ట్ కదా ఇది, మన లిస్టు. సార్ అన్నది జాయిన్ అవ్వడం వినిపిస్తుంది. నేనైతే మ్యూట్ చేశాను. ఏదండి చూడండి, ఇప్పుడు మ్యూట్లో ఉన్నాను నేను. ఇప్పుడు వినిపించింది, వినిపిస్తుంది. మ్యూట్లో ఉన్నాను నేను, వినిపిస్తుందా? ఇందాక అన్మ్యూట్లో ఉంది. లేదండి, మీరు ఒకసారి నేను మాట్లాడుతుంటాను బయట, ఒకసారి చూడండి. అంటే మీరు అన్మ్యూట్లో ఉన్నారా? వాయిస్ రావటం లేదు కదా. యూట్యూబ్లో వినిపిస్తుంది. యూట్యూబ్లో ఎలా వినిపిస్తుంది? దాన్ని మనం మ్యూట్ చేయలేము. ఒకసారి ప్రిన్సిపల్ గారికి చెప్పుకుంటాం. చేస్తాను అంటే ప్రిన్సిపల్ గారు వచ్చారు లేదా చూసుకోవాలి. సార్ ప్లీజ్ జాయిన్ సార్. రవి లాక్ అయిపోయిందా? నీది లాక్ అయిపోయింది. ఓకే ఓకే. ఎక్కడున్నా
3 dots ఉన్నాయి కదా.
సార్ వచ్చారు.
Good morning, Dr. Naidu.
సార్ గుడ్ మార్నింగ్ సార్. Sir, because our resource person also there, Kishore Kumar.
Hello, sir.
Sir, our principal, that is CLV RSU.
Namaste, sir.
Yes, sir.
So start చేద్దాం.
Please.
Yes, sir.
Good morning.
So thank you very much.
A warm welcome to today's speaker, our principal sir, vice principal sir, HOD sir, and my colleagues of GMRIT and participants. I'm Dr. P. Sumati Kumari, Associate Professor, BSNH, privileged to stand before you to present this International Faculty Development Program on importance of mathematics in science and technology. Now I request the convener of this today's International Faculty Development Program, Dr. R.L. Naidu, to give his inaugural address.
Thank you, madam. Our beloved principal, Dr. CLV RSV Prasad, respected vice principal, esteemed resource persons, and my dear participants, good morning. It is my great pleasure to welcome you all to this international FDP on importance of mathematics in science and technology. The objective of this FDP is to provide an intellectual forum for exchange of knowledge and information in relation to latest developments in the field of mathematics. Also, through this FDP, the resource persons will give information about how mathematics discipline is connected to different areas of science and technology. The significance of this FDP is to promote interaction between theoretical and applied areas. This FDP is equipped with eminent resource persons from various parts of the world who will be sharing their field of expertise with you. Mathematicians often say that the essence of mathematics lies in the beauty of numbers, figures and relations. And there is truth in that. Together with the experimental method, mathematics forms the conceptual scheme on which modern science is based and which supports technology, which with close interactions among them. Mathematics is like God, used everywhere. That is how each and every discipline is incomplete with mathematics. With these few words, I hope all the participants will be benefited with this FDP. Thank you all.
Thank you so much, sir. Now I consider it a privilege to request Honorable Principal Dr. CLVRSP Prasad to deliver the inaugural speech.
Good morning, all of you.
Good morning, sir.
At the outset, let me compliment and congratulate the entire team of Basic Science and Humanities, particularly from the Mathematics Department, for planning and executing this workshop on the topic importance of mathematics in science and technology. Though the topic appears to be more generic and covers the general domain, particularly looking at the engineering perspective, most of our engineering students, to my understanding, they learn mathematics for the sake of mathematics without really knowing the real application of mathematics and engineering and science technology. So understanding the mathematics with the background of the engineering and science and technology is more important. And I'm sure that this workshop will enable all the faculty members to enable them to visualize mathematics in a better way, so that all the upcoming aspiring engineers will really understand the mathematics as the fundamental requirement for any engineering. So without mathematics, there is no science. Let me tell like that. So when you talk about science and technology, so the science and technology doesn't exist without mathematics. But people learn mathematics as a subject, not really the basic concept. So this, I feel that it's a very right, apt topic that you people have chosen for enlightening all the faculty members, to make them understand that the mathematics is important for any science and technology graduate. Because in the first year, students learn mathematics, mathematical concepts in the various domains, without really knowing in which area they are being applied. There is no field in any of the domains, maybe in mechanical, electrical, electronics, civil engineering, computer science, name any discipline. Fundamentals are needed for mathematics, and to visualize and to represent a physical system, mathematics is needed. And the beauty of mathematics is any system, a physical system, can be represented by an expression. So in that context, people should really understand in what way the physical explanation of mathematics is needed. And when I'm saying the mathematics explaining as a theory, mathematics is being explained as some formulas and derivations and solving the problems, and the physical explanation of mathematics makes students more understand the real need and importance of the mathematics, particularly for the science and technology. So in that context, I feel very happy that this topic has been chosen, because this is an ever-burning problem for any mathematics teacher to make the students, first year engineering students, particularly to understand the need of the mathematics. Most of the students, they understand the mathematics importance in third and fourth years. They learn this mathematics in first and second year as a simple subjects, but they realize the importance in the third and fourth year, because they really walk through mathematics and a real application of mathematics in their engineering concepts. So I'm sure that this topic will make faculty members to understand very clearly about the physical concepts, and also make them or enable them to explain mathematics physically, and making the students to understand the concepts in a better way. So I'm I also thank all the resource persons who have agreed to be the part of this workshop by name, and then I thank for their time, and also I compliment all the participants that definitely at the end of this 3 days program, they'll have a lot many things to carry away and take away, where that will be useful for disseminating to the students. And wish you all the very best. Good luck. Thank you very much.
Thank you, sir, for your inspiring message. Now I request Dr. P. Murali Mohan Kumar to present the profile of today's speaker, Dr. N. Kishore Kumar, Assistant Professor of Mathematics, BITS, Hyderabad.
Thank you very much, madam. Good morning, principal sir. Head of the department, Lord my colleague. So it gives me an immense pleasure to introduce today's speaker, Dr. N. Kishore Kumar. He obtained his doctoral degree from IIT Kanpur. After that, he worked as a lecturer at NIT Warangal from 2006 to 2007. Then he joined as a postdoctoral fellow at Max Planck Institute of Mathematics and Sciences, Germany for 2 years. After that, he has been served as an assistant professor at IIT Gandhinagar from 2011 to 2013. Since then, he has been working as an assistant professor at BITS Hyderabad. So his specializations are numerical solutions to electric and algebra. He also completed 2 major projects of National Board of Higher Mathematics as a principal investigator. He gave several talks on various dimensional and information forums. He organized the national workshops and advanced planning program on partial differential equations. He also published various articles in reputed journals like Applied Numerical Mathematics, Journal of Numerical Mathematics, and Applied Mathematical Competitions, etc. So now I request Dr. Kishore Kumar to deliver the lecture on Tensor decomposition.
Okay, thank you. So should I deliver it now or should we wait
Yes,
for
sir.
the participants?
Please continue, sir.
Okay, should I start lecture?
Yes, sir.
Okay, first of all I have to share, right? I have to share my,
PPT, sir.
yeah.
Sir, that center button is there, no, sir. Arrow mark.
Yeah, I am looking for.
From left, third one, sir.
Okay.
Left, third one.
Kishore Kumar garu, thank you once again, Andy, for accepting our.
Yeah, thank you, sir. Thank you. It's,
Thank you, sir. Thank you. Sir Kishore garu,
Yeah, please.
you are able to open that, sir?
Yeah, I am able to open the file, but I have shared it, right? Okay, let me check. We have tested just a few minutes before.
First file, sir. I think your file is ready on desktop, no, sir?
Yeah, is it now? It is clear?
There, but that PPT is not visible to us, sir.
Oh, okay.
There is a pin is there, no, sir? Pin symbol. You click on that pin, sir. Automatically.
Okay, pin on my file or?
Top of your screen, sir. Pin is there, no, sir?
Okay.
Then only it will be visible to all the participants.
Okay. Let me check it. We have tested it just a few minutes before. It was fine.
Okay, sir.
Is it fine now?
Yes, sir.
Yes, sir, it is fine, sir.
Please
Yeah.
go ahead, sir. Please go ahead.
Okay.
Thank
Yeah.
you, sir.
So, thank you very much. So, thank you very much for giving me this opportunity to deliver the my lecture on tensor decompositions, and it's a good idea. So, for in these difficult times, people are not coming out, and then they're not able to hear any kind of seminar, and then this platform is very nice, and then the people have started doing these webinars, what's so called. People are throughout the world that started giving the webinars, and it's quite interesting. And of course, there's a communication gap will be always there between the participant and the speaker. whoever are participating and whoever are speaking. Definitely there is a communication gap. So the face-to-face is a different thing, and even classroom teaching is different from the online one. So, but anyway, so there is no option for us to interact with directly to them. But I hope the people will understand and follow the lecture, and I hope I will deliver it properly. Of course, there will be some technical glitches in between. So that is obvious because we cannot predict how the internet works and all. But I hope everything goes well, and then it will be successful. So really, as a principal of GMRIT told this, there is a gap between the science, especially engineering, and the importance of mathematics to the engineers, and there is a lot of deliberations and discussions have been took place how to go ahead. Even whenever, especially I will talk about the Indian scenario, whenever these new institutions, new IITs came up, because I was part of those institutions. I worked there as a, in sense when it was growing, and then we have a lot of deliberations about how we can incorporate or how we can generate the interest among the
sorry for the disturbance,
engineers, especially for the first years and second years, how to
Kishore, sorry for the disturbance, sir.
Yeah.
Is it in PPT mode, sir?
It is a PDF file.
PDF file, sir. Okay,
Yeah.
you, if possible, try to enlarge, sir. Complete screen, see that it will occupy a complete screen, sir.
Yeah, it is complete screen. I am able to see that.
Okay,
Can
sir.
you see that? Yeah.
Okay, sir. Okay, sir. No problem, sir.
Yeah.
Thank you, sir.
So then we have so many deliberations and discussions how to generate interest among these engineering students and all. It has been happening for several years, and but of course, as a teacher, we should start saying something. But as a of course, we are occupied with the, many other things, and then we are having some kind of a pressure to complete the syllabus, or they have to go for examinations, and then among all, adding all these things are not able to really convince them to or generating interest among them. That is my feeling. But anyway, this is not it is always debatable topic, but I am not discussing on that, but just because the point has been raised, so that's why just I put my opinion to others, but it is it's nowhere related to our topic. So coming to the point, so thank you for giving this opportunity, and especially head of the department, I thank for inviting me, and Dr. Murali for inviting me, and just he called few days back, and then he told me about this point, and then okay, I immediately agreed because okay. So let me start with my topic. So topic is tensor decompositions. It has it's a very the tensor decompositions. It exists in the literature for last 60, 70 years, but the people have started working on it, and really they are looking at the applications of it in the last 12 to 15 years only. There's a lot of work is going on nowadays in this area, because the people are looking for the big data analysis and this data mining and other things. The real people really started working in higher dimensions. So then they have looked at, okay, so we need to have to work with these really higher dimensions. Then we have to have such kind of environment, because working with the higher dimensions means your complexity grows like anything. So they suppose in each direction, if you imagine endpoints and you have d directions, that means d dimensions. So the complexity grows like this, order of n power d. I will show some examples to motivate you how what is the complexity and what is the curse of dimensionality. So as the dimension grows, It's called curse of dimensionality, because you cannot even imagine or beyond 3 dimensions. You cannot draw a 4-dimensional picture or really work in higher dimensions. Now people are working in really higher dimensions, like 100 dimensions, 150. We have really those problems arises in many applications, like in stochastic differential equations, the coefficients, because the stochastic modeling and all based on several factors. So let's say our economy or some kind of finance problems related modeling. So they have many factors which comes into the picture and influence the economy. So they will model it, and because let us say they end up with a differential equation, so which has a coefficient where it is depending on many variables, several variables like 10, 100, like. So such kind of data and such kind of scenarios are coming into the picture. That's why the people started working in the really higher dimensions, and then looked at okay, how to decompose them, how to find out the solution, how to work with it. In fact, so that scenario, so the people started looking at these tensor decompositions. Really, it has been lost, at least in last decade, from 2008 to 2000, of course, till today, the people, a lot of work is going on, and the really many applications people are looking at. So especially in data mining, big data, and stochastic differential equations, scientific computing, like many differential equation solving, or machine learning. So you can see that many books are coming nowadays, machine learning and linear algebra and machine learning. So tensor is for me, I look at it as, I don't want to look into the physical point of view, just you look at, understand it as a multi-dimensional array. So you talk about arrays, so single dimension, 2-dimensional arrays, matrix is a 2-dimensional array, 3-dimensional arrays, I, J, K. So like this, we have I1, I2, ID is my variables in I direction, D directions. Then you can see that we have a multi-dimensional array. So it's a D-dimensional array. So I will call it as a tensor. So in fact, if you want to store it, even if you want to store it, then you have to store n power d. It requires n power d objects you have to store in computer. So imagine d is even 15, and in each direction you have 100 points, 100 power 15. So you have to store that much huge data. So that's the problem. That's why big data computations and how to do it. And in many cases, suppose for example, if you look at let's say for the example of Chandrayaan, we have ISRO has sent to the moon. So then they take a pictures every second or every minute. They will send to the computers to the ground, and then we have to store it, the huge data, but we don't know what is the important information in it. So this is a huge data, and most of them is junk, but we have to extract the very important information out of it. So that is another problem. So getting the important information out of the junk or the huge data is another challenge. So these are the real challenges we are looking at. So all these we have techniques. So you people might have heard about PCA. The people, statistics people, mathematics people uses eigenvalue decompositions and principal component analysis. So that basically the principal component analysis do that. It extracts the very good information and more from the huge data and gives us, extract us the very important data. And once you have very important data, and then you can just remove the or delete the rest. So to extract the real information, very important information which is useful to us, we will extract that, and the remaining will be done. So this is the basic idea. So why people are working in the really higher dimensions, why we need to get it. So of course, in the talk I will start with motivating with a simple motivating example, and then really enter into the topic. So since it is a faculty development program, and I will keep my presentation elementary, not too elementary, but not too technical. So I don't want to give a too technical talk in the let's say in the given time, let's say 90 minutes or 1 hour 45 minutes, but because I want to give a flavor. So it's a new area coming up, and which is people are working in it. So just I will give a flavor of it to the people, to the audience, to the participants, and then at least let them feel okay. This is the area, and okay, this kind of work is happening. And then there's those who are interested. Really, I'll give some references, and then they can look after that, and then they can pursue their research or any kind of thing they can do, or improving the knowledge in that side. So basically, this tensor decomposition, as I said, tensor is a multi-dimensional array. So initially, the importance of first of all, it is a multilinear algebra. So we work with many variables. So it's a multilinear algebra. So the importance of linear algebra has been tremendously increased in the last decade. People start looking at, of course, it is existing and a very important thing in mathematics to understand everything. So first of all, even in any engineering courses, you can see that linear algebra is the basic course. But unfortunately, what we teach in most of the engineering institutions is only matrix algebra. So matrix computations, like solving system of equations, eigenvalues, and all. So of course, it is a part of linear algebra. Matrix is the main thing, the linear algebra. But to get deeper and deeper into that, we need to understand the basic theory of behind these matrices, and that's what called vector spaces and inner products, and then several other decompositions like the singular value decomposition and other decompositions. Today, most of the time I will emphasize on singular value decomposition. Okay, anyway, you are going to know that in few minutes. So singular value decomposition and other decompositions, how these are playing in engineering applications. So linear algebra is very, very, very fundamental and very useful, and a lot of applications in everywhere, in every part of mathematics and engineering sciences. Even if you started discussing about the ordinary differential equation and looking at a second order, let's say consider linear second order homogeneous equation, and then you know that it has two linearly independent solutions. So there itself you can see that the linearly independent vectors, right, you are looking at. So it goes back to the linear algebra. So the first course on linear algebra is very must, and it has wide applications. So in especially in computer science, it has a lot of applications, especially in machine learning nowadays. Data compression, data image processing, several such applications we have for the linear algebra. So first I will talk about the more I will introduce a tensor, and then most of my talk, let's say half an hour to 40 minutes, will be in dimension 2, that is right. So it's a matrix case, and then I move to the higher order tensors. So first of all, so this is my plan of the talk. Okay, so let us start the talk. So as I pointed out already, so what is all about? It is a tensor decomposition. Decomposition is already the title itself, decomposing something. What I am decomposing? A tensor. What is a tensor? Tensor is a multi-dimensional array. So if you, for example, if you discretize, so discretization is quite known to you all. Suppose I have a function f of x equal to sin x or cos x or e power x or any function, real variable, single variable function, and you have a defined interval 0, 1, let us consider. You take sin x, and then of course first of all what you do, you divide this interval into finite number of points. So let's say with the step size, uniform step size h is let's say 0.1, then the points will be 0, 0.1, 0.2 and something like 1. So we have 11 points including 0 and 1. So this is called discretization of a domain. So we will select some points on the, it will be uniform or any kind of randomly you pick up some points on this interval. So then you evaluate the function value at those points. Let's say sin x is evaluated at 0, 0.1, 0.2, 0.2. So most of you, because since you are a faculty and you might have studied a finite difference method, and you must be teaching that also to the engineering students. So, or a simple basic ILS method. So what you do is discretize the domain and evaluate the function value and function at those values. So you have a basically a discretized domain and you have a discrete points where the function is evaluated. So now imagine you have a rectangle or a square domain and you have a points everywhere on the square and then function is evaluated at that, and how do you store it in a form of a matrix? So it is a in each direction we have n points in this direction, ith direction you have n points, in jth direction you have n square points in total, and you store it in a matrix. It is an n cross n matrix. So you got a data of dimension 2. So this is a two-dimensional array. So now you imagine now cube. So we have three directions, I, j, k, and in each direction you have n points, and then you store it in an array which is three-dimensional array. A is my array, I, comma, j, comma, k. In each direction I have n points. So it is a three-dimensional array I have. So now imagine a d-dimensional box. The three-dimensional is a cube. Now you imagine a four-dimensional box or a d-dimensional box. Then you have in each direction you have n points. Then you have how many points? You have to store order of n power d. D is the dimension. So d is 3 in the case of 3 dimensions. Is 4, 5, 10, 100, like that. So it's a multi-dimensional array. So I will call it please mute. Somebody is. I'm listening some voice. Okay, so I have a d-dimensional array. So I have to store that. So in fact, I will come to that point. So basically, I'm working with a multi-dimensional array of dimension d. Okay, so what is a decomposition? What do you mean by decomposing it? So tensor decomposition is approximating the given tensor and sum of product of vectors. Vector is a one-dimensional array. So now I want to decompose this multi-dimensional array as sum of product of vectors. So basically, if you look or talk in terms of functions, it is basically approximating a multivariable function as sum of product of univariate functions, that means single variable functions. Let's say, for example, for understanding, f of x1 comma x2, it is a two-dimensional function, so it is not separable, let's say. So if it is separable, how it looks like? It is some function of x into some function of y. So you want to represent or approximate that function which is given as a two-variable function, for example, as sum of product of single variable functions, as a function of x into function of y. So this is the basic idea behind the tensor decomposition. So overall the idea is a multi-dimensional array is given to me and I want to represent or I want to approximate it as, or I want to represent it as sum of product of one-dimensional arrays, or that means vectors. So this is the basic point or starting point for the tensor decompositions. Now, so what is the use of it and why we need such kind of decompositions? Let me come to that point with the starting basic motivational example. So let us consider, so those who are electrical and communications students will be knowing, or even of course every mathematicians know convolutions. So if you have a convolutions of two functions, d-dimensional functions, k is a d-dimensional function, f is a d-dimensional function, then convolution is defined like this. You can see that this is my definition of the convolution, but anyway, I'm not going to the deeper into it since it's a motivating example. So this is I hope everybody knows the definition of convolution. And okay, how to find out that? So you know the very known techniques, which is fast Fourier transforms. There is a right. Using that, you have a code for it, and then you supply the functions to it, and then it will find out the convolution of these two functions, and it will give the output. Of course, what is the difficulty in finding out that? So basically, we look at the complexity. So how many arithmetic operations it requires to get the convolution on a digital computer? So it requires order of capital N log n. So what is capital N? Capital N is n power d. N is a small n, is the number of points in each direction. I have pointed it out and emphasized it already. N is the number of points in each direction. So we have n power d points. So therefore now you look at the complexity. It is order of n power d into something, log n power d factor. So if dimension is very large and you have in each direction very few points, it's impossible to evaluate on it within a period of time. So it's very difficult to work out with it and then finally getting the output of it. So then my question is, okay, it is impossible with a large dimension, huge dimensions, then it is quite impossible to find out this one. But so you have some flexibility. Or if you are damn lucky, or if you are very lucky, then suppose the function is already separated. That means you look at that in the box in the slide. If function is a separate function, that means it's a product of f of x1 into f2x2 f dx. That means it is already separated. K is also separated. Then what happens to this convolution in higher dimension convolution? This is a d-dimensional integration can be split into d one-dimensional convolutions. So you can see how easy it is. So you need to perform one-dimensional convolutions d times. So each convolution requires order of n operations, let's say. So then the complexity will be drastically reduced. Now you can see the complexity will be the power. In the originally, if you are working with higher dimensions, then the n power d. So whereas if it is separated, then you can see that d is coming as a product. So that is now the complexity is linear in d. So that is drastically reduced. Now where is n power d, and now is just linear in d now. That is the advantage if you have separated functions. Okay, always you will not have such luxury. Every given function is not given in terms of separable form. So therefore always you do not have such luxury, but you try to approximate it. Why can't we, given function can be approximated not exactly as a single separable function, sum of product of these in this form. Then you have still some product, there some k factor will also come into the complexity, but the complexity is drastically reduced, is an order of n dn only. Okay, so that is the advantage of having the separable form or in a approximation form also. So again, just to motivate, this is you can consider this example also. Again, the d-dimensional integral. So you have convolution is known. Okay, d-dimensional integral. So you have a d-dimensional function which is given to you, and you are integrating over a d-dimensional rectangle or a square or cube basically. So then you have integrating it. Again, the complexity is order of n power d. If it is separated, then you can see I can break in the box. You can see I can break the integral as the sum of the product of one-dimensional integrals, d such integrals. So now the complexity drastically came down to order of n, so d into n. So that is, so as I already pointed out, working with order of n power d operations is sometimes is quite impossible, because dimension is very large and number of points is very large, scoring itself is large. So that means, you imagine working with such arrays is quite difficult. And suppose I have two such multi-dimensional arrays, adding them itself. So how many entries I have to add? N power d entries, and entries I have to add. N power d entries from this multi-dimensional array and this array, d-dimensional array. So adding itself, it is quite impossible. So even in simple arithmetic operations like multiplication or multiplying with a constant the whole thing, it is quite difficult to work with it. So that is called curse of dimensionality, which I was mentioning at the beginning of this talk. So the curse of dimensionality is really bothering us. So only aim is, I have to drastically reduce the complexity, which is d is sitting in the power of n. We have to take it to the as a multiple of into d into something. So linear in d, I want to have such complexity. So this is the main, this is the motivation which I gave already. So what is the difficulty with these working with these tensors in multidimensional arrays, and how we want to drastically reduce. So it already given has given some ideas for us. What is a tensor? What is the difficulty with working with those tensors? And then where we gain, if you have some simple forms of the functions, then we have a reduce the complexity. So what kind of functions they are? If it is separable, that means separated as functions of individual variables, then it is very fine. Or even if you replace the function by the sum of products of it, an approximation, then also you will get a more closer and closer solution to the given problem, but with a very less complexity. So this is the whole idea of tensor decomposition is this. Of course, directly I cannot go and start with discussing, of course, for beginners, I cannot start explaining how we can decompose a multidimensional array. So let me start with a simple case, a matrix case, that is a two-dimensional array, is a tensor of order 2. So I will start with the matrix case, and then I will explain how we can do it in the matrix case, and then further go and see what kind of tensor decompositions we have for higher dimensional tensors. Okay, I hope you have followed until this point. So I hope I have conveyed the message, okay, what given what we are aiming at. Okay, let me start with the tensor and how I look at it as a tensor. A vector is a tensor of order 1. Vector, a long vector or a short vector. Vector is always a tensor of order 1. A matrix, as I pointed out, it is a tensor of order 2. It's a two-dimensional array. So d-dimensional array, I will call it as tensor of order b. Okay. So let me restrict for some time in dimension 2. That is the matrix case. So what we want a matrix to be represented as or approximated as sum of product of vectors. That is the idea. A given matrix is given, some matrix is given to you. I want to represent. Matrix means you hope that or imagine that it is coming from some discretization of a function or some other thing. So suppose if you take the image, the photograph, grayscale image, if you have a pixel matrix, it's already given in a matrix form. Suppose if you have a function which is defined on a square, and you have a discretized points, n square points, as I explained earlier. So the function is evaluated at those n square points. Then you have a matrix of n cross n size. That's it. So that how that will come. So I don't want to look at how it is coming about. It can come from any scenario or any modeling or anything. But I have a matrix with me, and how to represent as a sum of product of vectors. That means representing a function of two variables as sum of product of vectors. That is the idea. So you can look at in a discrete form, that is in the matrix way, or you can look at in the function form. That means a given two-dimensional function, how I can represent or approximate it as sum of product of vectors. This is the idea. So let us look at the matrix case. Start with the matrix, which is already a d-dimensional, a two-dimensional array, or you can call it as tensor of order 2. Okay. So now I will give a nomenclature here. So what I will call it as in the sum of product of vectors. I am talking about sum of product of vectors. The sum, how many sums are there? Let's say R sums are there. So then I will call that rank of that representation. So suppose I have a function. I represented it as sum of product of univariate functions. So how many sums are there? R sums. So then I will call that rank of that function is R. So that is the nomenclature. What is meant by rank is that the number of sums in the representation. Okay. Right. The question is how we can represent a matrix in terms of sum of product of vectors. That is the basic idea. So that is we have a very, very, very strong and beautiful answer in the linear algebra, which is given by linear algebra, is a singular value decomposition. I hope most of you have heard it, even though if you don't heard it, anyway, I'm going to talk about that. So it's a very, very powerful tool in linear algebra, which has several applications, even including computer science, data compression, image compression, data mining, machine learning. So there are latest books you can explore, machine learning books. So even by Gilbert Strang also, linear algebra and machine learning book. So you can see plenty of books are available nowadays. So you have this, what is the role of a singular value decomposition in it, or what is the role of linear algebra in machine learning. So the people really, you have plenty of applications for the singular value decomposition. So I start with the definition of singular value, or what is singular value decomposition. Okay, singular value decomposition, as I pointed out, it's the most useful and powerful tool in linear algebra. So I will take a matrix. It can be square or it can be rectangular matrix, or even I will consider real matrix. Even this decomposition is true for complex matrix. That means the entries are complex numbers. So I will start with consider the case of real matrix with a rectangular matrix. It can be square also. You can take the number of rows equal to number of columns. It is square. Otherwise, if m is rows are less than or greater than, then it is rectangular matrix. So M be a M cross N matrix, then you can see the box M is equal to U sigma is a matrix, U is a matrix, V transpose. So I can decompose a matrix as a product of U sigma and V transpose. What is U? U is an orthonormal matrix, V is also orthonormal matrix, and sigma is a diagonal matrix. You can see below the box I gave the representation of it. M is equal to U1. Bold U1 means it is a column vector. U2 is a column vector. UM is a column vector. That is U matrix. Each column is an orthonormal vector. So therefore it is an orthonormal matrix. So and sigma 1, sigma 2, sigma n are it's a diagonal matrix, and of course below the diagonal the entries are 0 because it's the rectangular matrix. If it is a square, just you have directly along the diagonal you have sigma 1, sigma 2, sigma n, and of course v1, v2, vn are column vectors of the matrix V. Okay, now what is the important thing is here sigma 1, sigma 2, sigma n are non-negative and they are arranged in a descending order. That means the sigma 1 is the largest one, sigma 2 is the next largest, sigma n is the least one. So they are arranged in descending order. So this is how. So given any matrix, you can write in this form. Okay. So those sigma 1, sigma 2, sigma n are non-zero, non-singular, non-negative, and they can be 0. Some of them can be 0. No such restriction is there. So they are called as singular values. That's why this decomposition is called singular value decomposition. Okay, what is a singular? Those things I'm not getting into it. So these are called sigma 1, sigma 2, sigma n are singular values, and those are arranged in descending order. So one can easily see, one can easily work out within few minutes. You can, if you take this product, matrix product, and you can see that the second this point m is equal to, I can represent it as I equal to 1 to n sigma I ui vi transpose. Now you see, I have started with a matrix, and then how I have represented it as the sum of product of vectors, right? That is the point which I have started with. I want to represent a matrix as sum of product of vectors. Same thing in higher dimensions. A multi-dimensional array can be represented as sum of product of vectors. So that is it. So how many vectors are there? Two directions. I have one direction. In one direction I have ui. In another direction I have vi. So I have m equal to summation I1 to n sigma I ui vi transpose. So now you see, my goal is I have reached my goal. I want to represent a matrix as sum of product of vectors. Okay, what are the advantages? I will explain. Okay. Okay. So therefore, and immediate application of singular value decomposition. The first application, it gives the matrix rank of a matrix. You know that matrix. What is the rank of a matrix? You know that number of linearly independent columns or number of linearly independent rows are rank, or you know from the intermediate level definitions also, you know it, rank of a matrix. Okay. So then you have see that, okay, you can see that if the rank is a rank, how it will give rank. So you look at the singular values. I have obtained n singular values, sigma 1 to sigma n. So you look at the how many number of non-zero entries are there in the singular values. How many non-zero singular values are there? Sigma 1, sigma 2, sigma n. More, some of them can be zero. That's what I have pointed out. So how many non-zero singular values are there? That is called rank. So immediate application of a singular value decomposition. Yes, sorry, just I will take the water. Okay. It's an immediate application. You can see the rank of a matrix. So then once I have the rank, because from sigma r plus 1 to, I have, let's say rank is r, so then first r singular values are non-zero, and from the rest of the singular values are zeros. So that means from sigma r1 plus 1, r plus 1 to sigma n are zeros. So then I can write the matrix in a simple form, and we can see the summation representation is from from I1 to n. It is only from 1 to r only. You can see. So that means only we have r such summations. So now you see, matrix is represented as sum of product of vectors. How many sums are there? R. So exactly it is since in the matrix case it gives the rank, so therefore it is a rank of the matrix. Okay. So in the complex case, U and V will be unitary matrices. That is anyway. Okay. Now already we have pointed out that, so we have such representations. I can represent as sum of. That's first question is, what is the advantage? What are the applications of this singular value decomposition? First thing is, most of you might have heard it. If it is new, it is. If some of you are listening for the first time, it is very surprising. In sense, imagine a matrix can be approximated by a matrix which is having a low rank. So far we have heard about the function which is approximated in terms of polynomials. So that is what you understand in interpolation theory. So a given function, you approximate it by polynomials. So here you are approximating a matrix which is having some rank R, and then I am approximating that one by a low rank matrix that is of rank k. K is less than R. So that means you can approximate a matrix by a low rank matrix. So that you can see here now, M can be approximated by M hat of rank K. which is less than r. How you can do it? Simple, very simple. So you remove those singular values which are smaller. That means, let's say you fix some rank, let's say k I want to have. From k plus 1 to r, you remove those, or just simply dump it. So that means only first k terms you consider in the summation. So that will be the exactly what will be the rank of the matrix M hat k, and you have approximated M by rank k matrix. That is the main important thing, main application of singular value decomposition. Okay, you have plenty of other, even in mathematics you can find a pseudo inverse, and several things are there for a singular value decomposition applications, but I want to emphasize much on low rank approximation. So matrix is approximated by a rank, a low rank, which is k, which is much smaller than r, which is approximated. Okay, fine. So whenever, even in interpolation theory, whenever you are approximating something, you always talk about, okay, if a given function I can approximate it by any polynomial or anything, if you don't bother about the approximation. But approximation means just not blindly approximating a function by some polynomial. So we need some accuracy. Okay, you have some purpose. So why you are approximating it? So you should be, my function or my polynomial should be very close to the given function, so that even if I replace this function by this polynomial, and if I want to integrate it or differentiate it, I should get a close answer as the integral of f of x or differentiation of f of x. So that is it. So how good is my approximation? That question we should rise here. So how good is my approximation? So that will be answered by these two norms. You can see this is given by Eckart and Eng, theorem, Eng and Eckart theorem, or Eckart and Eng. So it is a good approximation, not good, it's the best approximation in Frobenius norm and spectral norm. Of course, I am sorry for not introducing what is a matrix norm and all, but then it will be too elementary. So some things in these kind of talks one should imagine, okay, or should believe me. So if Frobenius norm and spectral norm, there is matrix norm you can define always. So in Frobenius norm, and that is f, in suffix there is a f, and in suffix there is 2. So in these two norms, it is the best approximation. Best in the sense, among all kind of approximation, it will give the best outcome. That is the best approximation. In these two approximations, my matrix approximation, this low rank approximation, using the singular value decomposition, is the best approximation. So there is no point of discussing it how good is my approximation. Okay, so just you can see that it gives us the best approximation in these two. Okay, applications of this low rank approximation. It plays a very important role. This has been very it plays a very active role in many applications. So you can see many works which are based on this low rank approximation. Even the example which I have cited and explained at the beginning, is Chandrayaan getting images from the satellite. So how to extract good data? So that where extracting the data, that means the data compressing. I am compressing the data. That means I am dumping the rest of the useless data and just only extracting the very important information out of that. So that is data compression. Okay. So data compression, data mining, image compression, machine learning, these are the applications of the low rank approximation. Okay, what is the advantage in approximating by a low rank approximation? I will show a few examples also. I will show some pictures here. So storage. Storage is the what is the advantage first of all in low rank approximation? Now imagine given matrix, you have M cross N matrix. How many entries you have to store? M into N. So Mn entries you have to store. Now, but in the rank k representation, that is M hat is equal to k summations of products of vectors. So how many singular values I have to store? K such. And k vectors each is of size m, u is of size m, and v is of size n. So totally you have, in total you have to store k into m plus n plus 1 matrix entries you have to store. When we have the advantage is if that product k into m plus n plus 1 is less than mn, then you have advantage. So you have an advantage in storage also. So basically we are compressing the data, only few entries instead of n entries you are having, storing only k into m plus n plus 1. So that is the advantage of the having a low taking the low rank approximation. Okay, here just I will share one more to show the simple example here. So takes a few seconds. Okay, where is this? I'll share one more file. Okay. Okay. Sharing. How to share another video? Okay. Another file. Okay. So, but I will explain it because I'm not able to share it properly. Okay, so suppose I will brief it. I want to show the pictures, but it is in another file. Sorry for it. So suppose I have a grayscale image. In example from image compression. Of course, even this is not a very sophisticated and widely used technique, a singular value decomposition for image compression. But at least to understand how data can be compressed, you can see. Suppose if you have a grayscale image, so that then you have a pixel matrix in your computer now. So suppose, so you have a pixel matrix which is of size something, let's say some m cross n. So then what you do is you apply a singular value decomposition to the pixel matrix, and then if you look at the singular values, what is normally happens in the, if you have a image, the first few largest singular values carries the most of the information, and the smallest ones does not influence much. That means you can dump all those smallest singular values and only use those largest singular values which carries the most of the information, and that means you approximate it by a low rank matrix, and then you reconstruct the image, and your image, the reconstructed image will be very close to the exact image. That means you have a lot of drastically reduce the compressed the image. That means the data compression you have done. So I want to show the pictures, but I'm not able to load that file. But anyway, I gave the flavor of it. Now even that is in the grayscale image. If you have a color image is we have three frameworks, RGB, red, green, blue framework. So each one is a face, each one is a matrix. So basically it is a color image is a three-dimensional array. So now what you do is you apply singular value decomposition to each one, each face, and compress them, and you can see the reconstructed images. So basically the most of the images, the first few largest singular values carries the most of the information. So just to motivate this, how it can be applied to the singular, how you can apply the singular value decomposition to compress the data. Okay. Okay, what are the difficulties with this singular value decomposition? I'd like to point out here. So there are several algorithms are available Several algorithms are available in the literature. But what is the difficulty? I'm not going to the details of how the algorithm works and all. So, but you can see the number of operation count. So how efficiently we can do it? What is the complexity of the computational complexity of this algorithm? It requires order of m power n square operations. That means if it is a square matrix, it is order of n cube. Order of n cube is in sense, if the n is very large, imagine n is a 5000. So 5000 whole square. So it is, if the, or let's say n is much bigger than that, then it is very expensive. If the data is very large, the algorithm is very expensive algorithm. But it gives the best approximation. SVD is the best. Okay. Finally, you can see the quote by this Stewart. I will read it. So, but that is one disadvantage. It is expensive. And another thing is, in some of the applications, you can see that in the decomposition, U sigma V transpose, U and V are some orthonormal matrices. They are not nowhere related to the columns and rows of the original matrix. We have some new columns and new rows. That is different, but it is. So, but we are not getting any kind of columns or rows from the original matrix. But in some of the applications, we need such representations. So that is another disadvantage for SV. But these are not measured. So because there is a scope of work for improving or to develop new algorithms. That's the only scope. So how do you do research? So you have some algorithm. Okay, somebody says, okay, this is the best algorithm. Nobody can beat it. But you should have something. Okay, you should have something in your mind. Okay, it is order of n cube operations. Okay, is there any algorithm which is good as this one? May not be the best, but which can be done with a less complexity. You can explore that. Then, so there is a scope here. So how efficient, how fast, there are any other algorithms which can do the same kind of work with less complexity. And okay, another one is, okay, my matrix in some applications, so I want these columns and original rows in my representation. So those things, those questions gives us several other algorithms, which I will just mention those algorithms. Okay, guys. So now we at least try to understand what is a singular value decomposition and what are the advantages of it. Disadvantages means complexity and all. And main application is low rank approximation we have seen. Now you see, I will give some references for it. Golub and Vaughan, those who want to read some linear and numerical linear algebra, there are plenty of books available in the literature. So Golub and Vaughan is a very standard book, so which is, both are computer scientists, also so written by them, and then it is a very standard book, and of course for the beginners it may be little challenging, but there are several numerical linear algebra books you can explore always. You just type numerical linear algebra books in Google, you can get plenty of material, and especially the singular value decomposition. In one such book by Stewart, he mentions that in the French, I think it is a French quote, but what is the meaning of it in English is the decomposition that all others try to beat. So it's the best, it is giving the best. So every other algorithm which tries to beat it. So that means, so that shows the powerful power of the singular value decomposition. A simple code which will explain the power of the singular value. Okay. What are the other decompositions available in literature? So QR decomposition is one such you might have studied when you are studying the linear algebra, especially in Gram-schematic orthonormalization. At the end of the orthonormalization, you will get a decomposition which is called QR decomposition. Everybody might know it. So, and another thing is rank revealing decompositions, UR decompositions, interpolative decompositions, non-negative factorization, semi-discrete decomposition. Especially these are popular in machine learning and image processing community. There are several randomized algorithms also, because most of the work as very important works are done by from the computer scientists from Yahoo Labs and other labs, those who have done the work in randomized algorithms. So these are some references which I gave, the review papers, and then you can see a lot of literature survey in it about the randomized algorithms also. But again, these randomized algorithms definitely will not compete with SVD, but it has again the complexity will be like this. So these are some other decompositions. Okay, now especially I will point out this decomposition here, Prass or skeleton decomposition. Okay, so I will take a 1 second break here. Drink water. So am I audible properly? And you are able to see the slides, but of course, unfortunately, I cannot directly communicate. Yes?
Yes, sir. You are audible and slides are very clear, sir.
Okay, fine. So everything is smooth, right?
Yes, sir. It's going well, sir.
And then for the participants also, it is streaming well, right?
Yes, it's streaming well, sir.
Okay, fine.
Right, sir. You can go, sir. Go ahead, sir.
Yeah. So should I take another 30 to 40 minutes? Is okay?
Yes, sir. Yes, sir. Please.
Okay. Yeah. Sorry for this disturbance.
No problem, sir.
Okay. So now, still I am in the matrix case because this is a very crucial step. This matrix approximation is crucial for the tensor decomposition. That's why, if I emphasize much on this, if you understand this at least to some extent, and then if I give a flavor in tensor decompositions, then you will have some, at the end of the lecture, you will have some flavor. Otherwise, if I start bombarding with the technicalities from the beginning, and then you are completely lost after 10 minutes of my talk, and then you cannot, nobody will understand in 1 hour everything. The only one thing is, you should get a flavor out of it. After listening 1 hour or 1.5 hours to my talk, you should get a flavor out of it. That's what I want to convey. I would like to give a flavor of it. So that's why I'm much emphasizing on the matrix case, and then I will quickly go through the multidimensional case. So here I'll point out, I will emphasize for next 10 minutes on this cross or skeleton decomposition. Is again, it cannot compare exactly, it is not as best as a singular value decomposition, but as I pointed out, it will give the very good, it is very close to the singular value decomposition. But one advantage of it is, you will get the, as I pointed out, you have this, in some of the applications you need the exact columns and rows of that, some columns it will use, and then complexity is linear in N. That is another advantage. Okay, first of all, what is a cross approximation or skeleton approximation? So a matrix can be approximated, or if in a nice case we have a nice decomposition, it can be equal. C is a column matrix. The columns are some selected columns of original matrix. That is the important thing. Whereas that one is missing in singular value. So the columns are selected columns of the original matrix. And R is a row matrix, which is K cross N, is of selected rows from A, original matrix. And G is the intersection of the entries in the intersection of these columns and rows. So that is a K cross K matrix. So now you have decomposed into C is a column matrix of size n cross K. G is a matrix which is inverse of the intersection of these rows and columns. The entries of this matrix are intersection entries. And R is a row matrix which is K cross N matrix. So then we can say that it is a rank K approximation of A. Okay, right. How good is approximation? Okay, I am taking columns from it, the original matrix, R from rows from original matrix, and I am constructing M, and then I am inverting it and finding out CCR. How close to the A? Accuracy, you can see that accuracy depends on the choice of M, how the good intersection matrix is. Otherwise, if it is not good in sense, which sense? Good in sense, while you are finding out the inverse, it should be non-singular matrix, right? So if it should be non-singular, so your choice of these columns and rows should be proper. If the choice is not, you are picking up randomly. So I will show that algorithm finally. So you pick up these columns randomly, and then if you pick up the randomly, and then you have rows also randomly, it will come, and then you have intersections, then it may be close to singular matrix. Singular means the condition number is very large, or close to singular means determinant is very close to 0. So there is a concept of condition number, because most of you know, but those who are listening for the first time, there is the condition number of a matrix, concept of condition number. So if the condition number is very large, then it is close to the singular matrix. That means the almost determinant will be close to 0. So such matrices you cannot invert. So your condition number is very large, that means your matrix inversion is very bad. It is not giving exact inverse of that. So if the exact decomposition is depending on inverse, right? M inverse is there. So if the matrix, your choice is not good, then your approximation quality will be very bad. So in this decomposition, the very important point is how to have a good choice of M. That a good choice is maximum volume submatrix. What do you call it as? Maximum volume submatrix. What is a maximum volume submatrix? Means, suppose you have a n cross n matrix. N is, let's say, 50, for example. A is 20, let's take. Now, out of 50 cross 50 matrix, I want to get how many possible 20 cross 20 matrices?
What are you saying? Filing
Hello?
Going on. Presentation is going on.
Okay. So there are plenty of possibilities are there. So 20 class, many such things. So among that, how to find out the good submatrix out of it? What do you mean by good submatrix? Which is having the maximum modulus of determinant among all those. So out of 50 class 50 matrix, you choose 20 class matrices and find out the determinant, and which is having the largest determinant, that is called maximum volume submatrix. So it is quite very hard problem to find out such matrix in a huge, let's say even 1000 cross 1000. If you want to find out a 5 cross 5 matrix submatrix which is having maximum volume, means which is having maximum determinant value, that is quite very hard problem. So it is again NP hard, that is close to the NP hard. So that is we cannot find out in that sense. So you can replace as in a good replacement is there, that is given in several such algorithms, which I will call it as adaptive cross approximation first. Okay, I don't want to talk much on this. So that iteratively we will add those sums of products. So that is another, that is reference is given to you. Now, yeah, this here I will emphasize what is called skeleton decomposition. That means I want to have a good submatrix which is having maximum volume. So we cannot get the exact maximum volume matrix, but very close to it. So suboptimal, basically we call it as technical line is suboptimal matrix. So that how to find that, it is given in this reference. is by Vasilevich and Teleshnikov. It's a Russian group which is given by how to find out a good submatrix. This is given in this paper. So using that, it is a very, you can quite easily you can find it with a less complexity order of n power k. N is the number of points in each direction. K is the rank, number of columns which I consider. So using that, you can find out the m, a good, very suboptimal m here, and then you can find out the representation C into m inverse R. So this algorithm works like this. You start with, first of all, what do you want? First C. So for that, I will show the picture here. You see that in the next picture, you imagine it as a matrix. I'll pick up some randomly. I have n columns in total. You pick up J1, J2, J3, some index of the columns. So I have picked up 3 such columns randomly. I don't know, I don't have any choice for it. Randomly I picked up J1, J2, J3. I have a matrix now. So now you write these columns as a matrix and store it in C. You have seen that C is this matrix which I have chosen randomly. Now what is our aim? I want to find out those rows such that my M is good. That is the aim. Only thing is, I said columns are from my original matrix, rows are from my original matrix. Only thing is, the important thing is choosing those intersections. That is, choosing those rows such that M is a very good matrix. Okay, that how to do it? So you can see that once we have this, as just now I have explained, this algorithm which is developed in this paper, how to find out a good submatrix, that will give you the rows, good rows. Here, I1, I2, I3, such that the intersection is good. Okay. So therefore, you see these the points in the intersection I have circled it. So these contribute to M matrix. So I have columns with me, I have row matrix with me. In the intersections, I have M matrix with me. So that all together gives us A equal to C M inverse R. This is my skeleton decomposition. Is it clear? Okay. So that is done with the linear complexity in n. Whereas see in singular value and all n power q, n cube operations. Where n cross n matrix. Here also n cross n matrix, but it can be done using linear complexity. You can do it, but it is not the best, but it will give as good as singular value decomposition. Okay, again there are some critical points here one can look for it. Okay, what is that? See, M first choice, initial choice of columns are not good, let's say. Then M may be bad. Even the algorithm which is giving good matrix, but it depends on the choice of J1, J2, Jm also, right? So if the initial choice is bad, the M will be close to singular. That means the condition number is bad. Then there are remedies for it. Okay, how to avoid that? Okay, first you randomly pick up some columns and then look for that maximum volume strategy, and then you get a matrix and look for the determinant or condition number of it. And then if it is bad, then what you can do is there is a remedy. So now you have rows also. Now you supply the maximum volume to the maximum volume subroutine, these rows, and then you repeat it several times until you will get a very good M matrix, so that it is quite easily or good, which has good inverse. So basically you have to switch over from first rows, and then you get a M which is having some good the determinant or a condition number, and then if it is not good, then you supply rows, and then you switch over from rows to columns several times. Several times means it takes a few iterations, and with a linear complexity. There are, of course, you are developing some algorithm means to a very good opponent. So you have some you are getting good thing means you have some bad replications of it also, bad points on that. So algorithm has this difficulty there, so that can be overcome by this. So several such remedies are there to improve the quality of this skeletal decompositions. But the important point is it is a linear. The complexity is linear in them, and the columns and rows are from the original rows of the matrix and original columns of the matrix. So this is the skeleton decomposition. So another thing is there. I don't want to explain it again here. Pseudoskeleton. Pseudoskeleton is basically in the M inverse. What you do is you find out the pseudo inverse of the matrix. That is again by singular value decomposition to a small matrix. But it can be done. It is also a good replacement for singular value decomposition. Okay, that I am not pointing out. It is also of complexity, linear complexity. So most of the things which I have talked about, you can take these class approximation and randomized algorithms and other interpolative decompositions and subselection, CUR decompositions, several decompositions I have talked about. Those things which are at one place, if you want to have a overview of those all decompositions, especially low rank approximation, in terms of low rank approximation of a matrix, you can look at our paper, which is published in 2017, Linear and Multilinear Algebra. It basically talks about all those decompositions, starting from singular value decomposition, advantages, disadvantages, randomized algorithms, and then class approximations and several things. And then just you can have a look at this paper, or at least to have an exposure about the low rank approximation of matrices. Okay, finally I just show two examples to conclude with, at least in two-dimensional case, and then I'll move to the tensor case. Okay, so how it is my, of course here I am taking the not skeleton, pseudoskeleton, which I have not explained it here, but anyway it will give, you can easily understand how quick it is in comparison with the singular value decomposition. Suppose I have a function like this, a two-dimensional function, 1 by square root of 1 plus x square plus 1 square, the square domain, unit square, and then in each direction I have 5,000 points on uniform grid, and then if you apply the singular value, skeleton decomposition, you can approximate it with rank 8 up to 10 power minus 14 accuracy. It's very, very close to the exact function. This. So it simply takes 0.15 seconds here, whereas singular value decomposition takes almost 615 seconds here, and that will take around 600 seconds or more than that singular value decomposition. Of course, this is a very smooth function. Suppose even if you consider the singular function, that means very close to the singular function. So then here also up to rank 14, you are able to approximate it to 10 power minus 12. This is the last column of the last row of this table, 10 power minus 12 with a very few seconds, whereas singular value decomposition takes 1000 seconds. So it's very quite fast because of the complexity. Whereas singular value decomposition is of complexity n cube, whereas this is order of linear in n, so that is order of n, k into n. So that's why it is very fast and good approximation. With singular value decomposition, it may be around 10 power minus 14 or something, but here 10 power minus 12, very close. And then you have an advantage of time here, linear complexity. So this is about some decompositions for a matrix case. Right, now I will move to the higher order tensors. So I started with what is our task, or what we are trying to understand here, and then our aim is looking at the higher dimension tensors. But initially we have started with the matrix case. How we can do represent a matrix as sum of properties. That's what we have understood. Algorithms, several algorithms we have understood. Now we'll come to the point, the tensor case. Tensor case, okay, before going to that, what are the applications of tensors? As from the beginning itself, I am emphasizing real applications, and nowadays how the people are working in higher dimensions, right? So So there are plenty of applications of tensor decompositions. But of course, before starting the discussing, you can explore these kind of literature surveys of tensor decompositions. You can look at this, the initially very good review paper in Sham Review. So in 2009 it has appeared. So it's from some USA, some Tamara Kolda and her team. They have done a good research in this area, tensor decompositions initially. So tensor decompositions and applications is a review paper, around 40 pages, almost 45 pages. Gives complete review on what are the tensor decompositions available by that time, by 2009, starting from 1920s. So it's a good, good review paper. And then again in 2013, it has appeared in the literature survey on low rank. So from 2008 to between 2008 and 13, there is a lot of work which has happened in tensor decompositions area. So it includes all those literature. So by the time to 2008 to 2013, there are a lot of algorithms they have developed in that period. And after that, almost from 2011 the people started looking at applications of those algorithms. So by that time they have developed the algorithms for tensor decompositions. And then later, from 2012 to till date, the people are looking at the applications of tensor decompositions in several above mentioned areas, like even in higher order partial definition equations, stochastic PDE, Schrodinger's equation, solutions of computational homogenization, all those things. And this is the first, the kind of test book which is appeared in 2012. And at the end, I will quote or give references about the recent test books and monographs appeared in last 2-3 years. So that means it's a very quite a new area. A lot of work is happening in this area. So now I will start with some existing tensor decompositions. Okay, I will give a flavor of it. I don't go into the deep as singular value decomposition or skeleton decompositions. I'll point out these how it works, and then I will explain how these matrix decompositions can be used to find out the tensor decompositions. Okay, initially it goes back to 1927 and 1970s work by Horstman and Carol John, 1970. So this they are specific to different names in the literature. In some articles they call it a CP decomposition. In some of the literature they call it as canonical decomposition. And in some literature they will call it as parallel factors, that is para-fact. So all are known for canonical format. What is called canonical? It is very similar to the instance. Technically and mathematically it is similar to the singular value decomposition. So it is split as sum of product of vectors. So now you say it is a three-dimensional, draw a three-dimensional cube here. In each direction I have n1, n2, n3 points, and then I will represent it as sum of product of univariate vectors u1, u2, u3, right, in the suffix, right. So therefore you write it as sum of product of these. Okay, this is a canonical standard, just similar to technical, mathematically similar to the singular value decomposition. Here, the disadvantage here is there are no proper very good algorithms. So there is one algorithm which is called alternating least squares algorithm, which works fine, but if the dimension is increasing, then there is the complexity is very large, and the matrices which is coming out of that will be very high, having high condition number. So there is no, in sense, good algorithms available in the literature for the canonical format. But it is as in the literature for since 1927. So another quite popular decomposition is or format is Tucker format. Tucker format is a little different. It looks different from the canonical decomposition. You have a core tensor, which is again a d-dimensional tensor, but size is very small. And you have orthonormal matrices. This is a three-dimensional picture. So orthonormal matrices. So you have a decomposition which I have explained. Okay, I'm not going to details of this, every technical details of it, but the symbol is stands for the tensor product here. So this is how the Tucker format looks like. It's not very easy to explain it in few minutes. Let's say 10 minutes or 5 minutes. So that's why I'm skipping this. But this is also a very popular tensor format which is available in the literature. But there are good algorithms are available. Higher order SVD is there. So it's developed by Latover. He's from Belgium. Developed by this group. And alternatively, square method works. Then Newton's iteration algorithms and several algorithms are available. So very good algorithms are available, and it is also very good tensor format. But the thing is, again, as the dimension increases, the core tensor, which is B, which is drawn in the blue color here, which is again d-dimensional tensor. But, of course, even though size is smaller, but the dimension increases, so the complexity definitely increases. That is the disadvantage with the Tucker format. Then there's a format which is called a tensor train format. This is the one which is a very popular nowadays, and very quite easy to implement it. And they have MATLAB toolbox for it. Those who are interested, they can download it. I will give the reference for the toolbox where it can be done. Download it. You can easily work with it. They have a huge package of subroutines and everything, how to work with the tensor train format, and really applications of tensor train format in many things. So they gave some examples of solving a higher dimensional Laplace equation. Let's say example in 50 dimensions. If you want to solve a Laplace equation with bounding, a directional bounding condition or something in a rectangular box. So then how to find out using this within few seconds. Imagine, so if you want to work with a really higher dimensions, it requires huge time, let's say years. Then it can be done in few seconds, just solving such equations. So, and which is easy to understand this format is, and then you have a whole package, a toolbox for it, and then very nice applications. I will give the references for the applications just to explore it, and then you can really go through it and start working in it if you want to pursue something or do something in this area. So the thing is, the idea is why it is called tensor train. So this is a picture is of a 4-dimensional tensor. You can work for any dimension here. So now you see V1, V2, V3, or you can replace it by I1, I2, I3, I4. These are the variables. The edges are the nodes are stands for the variables, and edges are how we connect through the rank some matrix. I will explain it. So now you see they are connected like just a train. So one bogies, right? So this, right. So these are connected like this. That's why it is called a tensor train decomposition. So this has very recent in sense 2009 they have developed. It's a Russian group. So oscillators and Devchishnikov. So they come up with this one, and then it is a complexity is linear. So how this works is just a sequence of matrix decompositions. You use it. The decompositions which we have learned just now, skeleton. So a sequence of skeleton decompositions, you use it, and then you construct the tensor train decomposition for a d-dimensional tensor. That means splitting it as sum of product of univariate values. Right? So I'll brief the algorithm. It's quite easy to understand. In sense, at least getting the flavor out of it. But of course, technical details will be there. Details will be there. but at least it will give, okay, how it works, roughly how you construct such a approximation. Now you see, you consider as an example a fourth order tensor, I, comma, j, comma, k, comma, l, each direction. We have 4 directions. In each direction I have n points. So it is n power 4 storage. It's a 4-dimensional array. So first what you do is, there is a concept called vector matricizing a tensor. That means, or technically it is called unfolding, or in a simple language it is called matricizing. So matricizing a tensor. So how we can matricize a tensor? That means A is a 4-dimensional tensor. So I will reshape this a long matrix. Of course, it is for only theory. In technically or in the algorithm, we don't do it literally. So working with n power 4 is difficult, right? Or n power d is difficult. But technically for algorithm, in our mind, what is happening? We are doing our matricizing. So I will write it as I rewrite this whole tensor as a long matrix. That means I rows, but j into k into l. That means n cube columns. That is a huge long matrix. So now we have a matrix with us, n cross n cube matrix. Apply the skeleton decomposition, which I have explained. First select columns and obtain the maximum volume, you get rows, and then combine them, you will get a skeleton decomposition. So skeleton decomposition, so then what I do is, I separated these columns first. That I will store it in G1. How many such columns? Alpha 1 columns I have. Now, remaining on the next long matrix, I have how many more total? It is again a tensor which is having alpha 1. Out of I have selected alpha 1 columns, right? So rows also, because max volume technique will give rows, alpha 1 rows. So I have alpha 1 rows, j, I, k, l, this one. Now I left out with, I will store it as G1 and I will point out only on A1. I will concentrate on A1 only. So now A1, I will rewrite it as alpha 1j, comma, KL matrix. And then again apply the skeleton decomposition, which can be done linearly. So again I have G2 here. So which depends on alpha 1 and also new alpha 2, that is rank k, right? New rank. So alpha 1 and alpha 2. So similarly, I'll do it for A2, and then finally you see the expression at the end, A is approximately equal to alpha 1 to R1 rank of that skeleton decomposition, for particularly in that unfolding. R2 is the second, in the second step, R2 is the rank, R3 is the rank in the third step. So then finally I have this format. So now you can interrelate with the picture. So now you see the first term G1 is alpha 1. In G2, this one is connected through alpha 1 and alpha 2. That is what exactly you can see in the picture. In the C, the edge J1 is correspond to alpha 1, J2 is correspond to alpha 2. This index V, here in the example it is J, is connected to V1 through alpha 1 and V3 through alpha 2. Similarly, the edge. So therefore, now you have that representation, tensor train representation. So now you see how we have done that by using sequence of matrix decomposition. Yes? Pardon? Okay. So this one is decomposed like this. Okay. So I hope you got the point. How in higher order tensors we use only the matrix decompositions which we have learned, skeleton decomposition or other decomposition. Use it sequentially one by one, and then you constructed the tensor decomposition. So you have separated variables finally. So I, j, k. Here it is. The third one, G3 is k. Sorry, is a typo. So is k. So therefore, I have decomposed like this. So it can do it in with linear complexity. Okay, that is. So now these are some references for this tensor train decomposition. It is first proposed in this paper, Linear Algebra and Applications in 2010. It is appeared in, and further how to operate with these two tensor chain formats, adding two tensor chain formats, multiplying or some other algebraic operations with the two tensors which is given in tensor formats. Tensor chain formats can be how they can be added or how they can be multiplied and all those things. Basic operations which is given in, and the tensor toolbox, train toolbox, MATLAB toolbox, which is given in this web address. We can easily download it and quite easy to add it to your MATLAB toolbox, and then you can read it. And there is a you can read. There is a manual how to work with working with some examples, higher dimensional integrations. They gave some 150 dimensional integration also in that examples, and then you can easily work with that. Applications, as I said, machine learning, neural networks, other things. So there are other formats, which is a hierarchical tensor format by Hagbush and Kuhn in 2009, and by our group, this tensor chain decomposition we have developed in 2012. Okay, this is all about tensor chain decomposition. I hope I gave a flavor of it, but of course, in just 20 minutes I cannot give a complete picture of it. But at least what you have to understand is just how you use the matrix decompositions to get the tensor decompositions. So this sequentially you apply these decompositions to the tensor and get the final tensor decomposition. Okay, so it's almost I have talked about 1 hour 40 minutes, and then just quickly within 1 or 2 minutes I will give another new format which is called QCP and QTT format, and then I will conclude this talk. Okay, so imagine in many applications like in stochastic and all, where the coefficients, there are some difficult even one-dimensional functions, single variable functions like Gaussian. Gaussian is e power k minus kx square. This is like a bell shape. Whenever you are talking about probability and statistics, you know it. Normal function, right? Normal distribution function. It's like a bell-shaped function. Those are called Gaussians. So e power minus kx square. If a k is very large, then it is a very sharp. You must be heard of this Dirac delta function. So it's a very sharp, and it has one particular value at one point, and everywhere it is. Such kind of peaks, mountain peaks will be there in the Gaussian functions, and very highly oscillating functions like sine kx. K is something like 10x, sine 10x, sine 20x, 25x, or something like very highly oscillating functions, or very singular functions like square root of x, right? So those functions, even you have some idea about interpolating polynomials, Lagrangian interpolation or any other kind of interpolating polynomials. So whenever you approximate that in a unit interval, let's say, for example, in -1 to 1, you try to approximate e power minus kx square, and try to understand. It's just I'm giving it as an example, and you try to approximate x power half, square root of x, or x power 2 by 3 in 0, 1 interval. It's a very singular function. It's a singular function close to 0. You try to approximate those functions, then it is quite difficult to approximate very well. That means to good accuracy you cannot really approximate until unless you have a very fine mesh. Your mesh size will be very close to 0, or you use any geometric mesh or some other mesh, different mesh, and then try to approximate it. So in such cases, you need a very fine mesh. That means a huge mesh, 2 power, let's say of size 2 power minus 15, 2 power minus, that means h size, very close to 0, very, very small size. Then in such case, you have a huge mesh. So if you have a very refined mesh in each direction, then you have a huge data in higher dimensions. For example, if I take the example of e power minus x in 0, 1 interval, and I have considered the interval 0, 1, and I divided uniformly into, let's say, 16 points, right? And then I took the function value e power x at those points, then I will just denote q by e power e minus h. Then the function value at those 0, h, 2h, 15h will be 1, q square q15. It is a vector of size 16. So length n power 16, n power 4. Now what I will do, this vector, I will reshape it as a tensor. Now we are thinking of vectors are easy to work with, but now what we are doing, I reshape it as a tensors of a 4-dimensional tensor, the 2 class 2 class 2 class 2 tensor. And then what you do is, what you can see is, if you find out the canonical decomposition of this Q, the reshaped tensor, you can see it is quite easily represented as 1Q, tensor product of 1Q square, 1Q4, 1Q8. So now you see, only I need to remember 4 entries. I am able to represent whole vector by using 4 entries only, Q, Q square, Q4, 4, Q8. So with this, I can work with this vector, whatever I want to do, and then I can conclude whatever I want. So that means how drastically this the scaling is reduced. You see, where is n power d, for example, d dimensions, n power d, and where is log 2n. The drastically the scaling is come down. So now you see, in the general case, this is my scaling. In general, even for e power minus lambda x, how I can represent with L parameters only. Instead of 2 power L, I work with only L parameters. That is called quantizing. That is called this is quantix, basically quantix canonical format. There is again a quantix TT format which has been developed in 2011 by Boris Koromsky, and this is given in this paper. But of course, I want to emphasize, only thing is, you given the vector, you reshape it as a tensor and apply the tensor train decomposition to it and work with it. So yeah, it has exact representation, tensor train representation for these functions. E power minus x, the rank is 1. E power f of x, rank is 2. F of x square is 3. Sin x 2, cos x 2, like this. You have exact representation for such kind of functions. So there's plenty of applications for this QTT format. And QCP, we have recently developed the collaboration with Boris Koromsky. This is appeared in Numerical in algebraic applications in 2019. So this is a QCP format which I have presented. So similarly, the QTT is quite old, in sense not very quite. It is appeared in 2011. It has wide applications, and people are started using it in different formats. Okay, so I would like to conclude the talk by giving some references. Latest developments, you can see that there are some manuscript monographs or textbooks. So tensor numerical methods in scientific computing, what are the different fields this is used, and tensor numerical methods in quantum chemistry, especially in quantum chemistry, is basically you look at for the molecular interactions. You have several molecules, they interact each other, where there these, of course, more complicated structures will appear. The tensor train is just this kind of structure. So where there is a tensor network structures, they are connected like they are connected. So one, if you imagine one molecule as an edge, and then it is interacting with several molecules, then you have edges with the other molecules. Then you have a complicated network structure with these in between the molecular molecules. So therefore, you have more tensor network structures you need. So that is also people are working. There are many popular tensor networks available in the quantum physics and quantum chemistry community. PEPS is one such network with very popular networks. Matrix product states, which is also very known in their community, matrix MPS, and PEPS is also very known in the community of quantum chemistry and quantum physics. So those, at least those, if you want to look at those kind of applications, you can look at those first two books. And especially in computer science, machine learning, or neural network areas, you can see these very recent books in 2016 and 16. Again, this is even oscillators is there, is a part of that group. Sichoki is very famous in the community. So these two books are part 1, part 2. In machine learning and the neural network community, they came up with new books. And especially you want to look at the tensor train applications in mathematics and communication, computer science. You can look at the even oscillated books, Numerical Tensor Decomposition is a very recent book, 2018. So these are some new recent advances and recent manuscript monographs of textbooks in this community. And you can have, explore any tensor decomposition. You just type in, you can have plenty of applications. Several people are working on recent papers, very recent papers you can see. And tensor completion is another new trending word in the recent 2-3 years. Tensor completion also, you can look at that. So these are just, I tried to give a more a flavor of what is happening in a very recent area, very new area. So, and I hope I have conveyed the message, what I want to convey, and I hope you have enjoyed. But of course, one disadvantage is I cannot personally interact with you and talk to you. And if you have any questions, just as the organizers point out, just write to them, and you just get email from them also, and write to me for any references or any information on this area. And of course, Google is there. Nowadays, it's not a problem to get any kind of information. And thank you very much once again for the organizers, and I really enjoyed. Thank you very much.
Thank you, sir.
Yes.
Thank you,
Yeah.
Kishore Garu.
Yeah.
1 minute, sir. Just 2-3 minutes for participants' questions. Dear participants, if you have any questions, please post in the chat box. We will read out those questions, or will answer those questions. We will wait for 1 or 2 minutes only.
Yeah, okay, fine.
Yes.
Otherwise, let them write to my email or to you, and you just apply.
Sure, sir. Sure, sir. Some of the postings, let me read out. So
Yeah, please.
one question, sir, they have posted. Is Riemann tensor works with 4th rank tensor?
Which tensor?
4th rank tensor. Is Riemann tensor works with 4th rank tensor?
Yeah. See, just as I pointed out, if it is, I pointed out in terms of a multi-dimensional array. If it is a fourth order tensor, these techniques will work.
Achha. Any other questions?
Any d-dimensional array.
Okay. I hope participant you got the answer.
Or just ask him to explore it, and you can easily explore it.
Yes.
If it is personally, then you can interact much.
Okay. I think they have no question, but they have given very good feedback, sir.
Okay.
Nice session, very enlightening one, and useful for researchers.
Yeah, that's what I thought. Just doing a lot of technical details it doesn't make sense. So give a flavor of it and just generate interest in them.
Sir, actually, this decomposition related things, many CSC people have asked me, sir, being a mathematician,
Yeah.
they have asked these decomposition related things, sir. Very useful for CSC people as well as the research who are doing with computer related things, no, sir.
Yeah, that's what I said. You just type this, and then you can see recent developments in big data and machine learning, a lot of applications.
Yes, sir.
Coming up with books. In very recent, Gilbert Strand came up with a book, linear algebra and machine learning.
Yes, sir. Yes.
So we can see that this is singular variable decomposition and other decompositions, how they are useful in those areas.
Very interesting, sir. Good talk, and it is about almost 2 hours talk, sir, for yours.
Almost.
Hats off to your energy levels, sir.
Oh, no.
Thank you very much.
If you have any recorded,
Yes, sir. I will share you, sir. I will share you. We have recorded the total thing.
Okay, I hope participants have enjoyed.
Enjoyed, sir. Enjoyed a lot. They have given very good feedback.
How many were there in stream?
Total 200.
No, sir, around 300, sir. 300, sir.
300.
Okay,
sir.
fine.
300
Fine.
It is now
participants.
302 in YouTube live, sir.
Okay.
309.
Okay.
Dear participants, in a short period, we are sharing that feedback link. Please wait.
Okay.
Please wait and fill the feedback link.
Oh, I have to fill?
No, sir. For you, not. Kishore Garu, thank you very much for your valuable time and enlightened us very much, sir.
Yeah.
I hope maximum because of their we have gone through the total feedback. They appreciated really about your talk.
Okay.
Thank you a lot, sir.
Yeah, thank you. Yeah.
Thank you. I will meet you, sir. Thank you.
Yeah.
Sure, sir.
Yeah.
Thank you very much, sir, for your lecture.
Oh, okay, thank you.
It is my really humble request. Again, thank you, sir. Thank you very much, sir. From our department.
Okay, thank you.
All is that?
Okay, I'm leaving the meeting, okay?
Yes, sir. Thank you very much, sir.
Yeah.
Yes. అవునా నేను క్లిక్ ఇస్తాను
రాబాబు గారు చెప్పిన ఇష్యూ జరుగుతుంది ఇక్కడ.
అవుతుందా
రాబాబు గారు లాస్ట్ టైం వాట్సాప్ చెప్పారు.
అవసరం లేదు నేను చెప్తాను. Dear participant, please wait. I am posting that link. నేను యూట్యూబ్ ఆన్ చేయాలా మళ్ళీ? లైవ్ చాట్ ఎంత నేను పోస్ట్ చేస్తే సరిపోతుంది కదా. మీకు ఇచ్చిన లింక్ మేడం వెళ్తాను. మీ వాట్సాప్ షేర్ చేసుకుని వాట్సాప్ యాప్ యూజ్ చేయండి సార్.
సార్ నేను పంపిస్తాను సార్ ఫీడ్బ్యాక్ ఫామ్.
ఓకే ప్లీజ్ బికాస్ పార్టిసిపెంట్స్ ఆర్ వెయిటింగ్.
కింద ఐడెంటిఫై అవ్వలేదా?
నేను పేజ్ పంపించాను చూడండి. యూట్యూబ్ లింక్ వచ్చిందా? ఎవరికైనా వచ్చింది?
పంపించండి సార్.
నేను కూడా పెట్టాను చూడండి. Participants, please fill the feedback form posted already in the chat box. And thank you for attending. We will wait for another 5 to 10 minutes. Within that time, please fill the feedback. చెప్తాను మా వాళ్ళు చెప్తాను.
యూట్యూబ్ ఫాలో అవుతుంది చేస్తాను
FDP లింక్ అంటే
ఛానల్ బట్టి
యూట్యూబ్ ఈ రోజుది యూట్యూబ్ ఒకసారి ఈ నెంబర్ పోస్ట్ వచ్చింది కదా చూడండి, మీరు ఓపెన్ చేయండి. ఓపెన్ అవుతుందా?
టైప్ చేస్తాను.
Participants, please fill the feedback form. We will wait for another 5 to 10 minutes only. కనీసం మీరు కూడా చేయండి, చేస్తే దాని డిఫికల్టీస్ తెలుస్తుంది.
సార్ మన వెబ్సైట్ స్టార్ట్ బాక్స్ లింక్ మన వెబ్సైట్ స్టార్ట్ బాక్స్ ఒకసారి వెబ్సైట్ స్టార్ట్ బాక్స్
మీన్స్ 4 అని వచ్చింది సార్.
Today's link.
ఇదే ఫీడ్బ్యాక్.
లేదు సార్, 2 days సార్. Also, we will receive a fundamental certification. Thank you for submissions. Everything is good. Very good job. And now, good question.
డిలీట్ చేసింది. ఇది షార్ట్ ఫామ్
మీ వెయిటింగ్ వచ్చేసింది సార్. మేము వచ్చింది అది వస్తారు, అదే చెక్ చేస్తున్నాను. నేను పెట్టి చదివి పని చేస్తున్నాను. ఆల్రెడీ రెస్పాన్స్
లింక్ నెక్స్ట్
కానీ నంబర్ మీరే ఉంది సార్. కానీ
యూట్యూబ్ లైవ్
నేను కాపీ చేసుకొచ్చాను సార్.
యూట్యూబ్
నో ప్రాబ్లం, నేను స్టార్ట్ చేస్తాను. చేసుకోవచ్చు,
స్టార్ట్ చేస్తే
హైలైట్ వస్తాయి.
యూట్యూబ్ లింక్ పెట్టాను, ఈరోజు యూట్యూబ్ లింక్ పెట్టాను. ప్రసాద్ ఓకే వినిపిస్తున్నాయి కదా. ఓకే
వచ్చింది వచ్చింది సార్, వచ్చింది నాకు.
Dear participants, thank you very much for participating on the first day, and tomorrow we will resume at 11:15. 11:15. Please join for day 2 session, and thank you all.
Thank you, sir. Thank you. మరి ఇక్కడ
మనం వీడియోస్ అవి ప్లే చేయాలంటే
అది ఆటోమేటిక్ గా కొన్ని మెసేజ్ చూపిస్తారండి.
ఎట్లా
వెబ్కామ్ ఉంటుంది కదా సార్, చెప్తారా?
ఇప్పుడు చూడండి. ఇది మోసు ఇది మోసు
ఇది ఉంది కదా సార్ ఆల్రెడీ.
ఇది నేను ఇది విజిటర్.
అదే రేపు వాళ్ళు ఏం చేస్తారంటే
ఇక్కడ